morning. Today we will start a new chapter, Thermodynamics of reactive systems. Now, when the reaction takes place, as you know, the new species are formed. So far what we have discussed in thermodynamics, that the process takes place between different species where the species remain unchanged. There is no formation of a new species or no depletion of an original species. But when reaction takes place, chemical reaction, you know, from some original species, some new species are formed. This is because of the breaking of interatomic or intermolecular bonds and the readjustments of the atoms, molecules or electrons, whatever you say. We are not going into that deep. The new species are formed from some old species. So, this is basically how we can define a reaction, chemical reactions classically. Now, in this case what happens, since the new species has formed from the old species, the analysis is almost the same but with a little different approach. Now, let us concentrate that, let us how we represent a reaction. Just a simple case, let us consider a reaction like that. Two species A and B react to form two species C and D. If a reaction, chemical reaction is expressed like this, that two species react with each other in a conducive environment when the reaction is possible and produces C and D. In that case, there are certain terminologies. This A and B, the original species, known as reactants. Reactants. These are the terminologies you have to know. And the species which are formed out of these two species, that means out of the reactants, are known as products. So, therefore, always we tell or we write a reaction symbolically as reactant to products. The reactants may constitute different species and products may constitute different species, but as a whole, these species which are being formed as known as product, and the species which react, that initial species, to form the products are known as reactants. So, reactants to products. Now, as you know that when this reaction takes place, the total mass of the reactants must be equal to the total mass of the products. So, before that I must tell this way, that will be better, that for these reactions the conservation principles, the conservation of mass and energy has to be obeyed. That means conservation of mass we write. So, they cannot violate the principle of conservation, mainly the conservation of mass and conservation of energy separately, since the mass and energy conservation, from mass to energy and energy to mass, is excluded. So, therefore, as we have done for other processes and reacting processes also, for a chemical reaction also, conservation of mass and conservation of energy have to be obeyed separately. Now, we will discuss that this is conservation of energy, as we know, is the first law. First of all, I tell you the scope of this first law of thermodynamics, which will deal with the conservation of energy. The second law of thermodynamics will be applied to find out the direction in which the reaction will take place. As you know, for any process, the conservation of energy, as the first law deals with this thing, that how much heat has to be removed or how much heat has to be added, how much work is done or how much work is added for a process to change from one state to other state. But whether a process will take place in a particular direction, whether from one state another final state is achievable or not, or if achievable, what should be the directions in which it will be achievable, these are the information which are furnished by second law. So, therefore, we must know that even if the conservation of energy is there by the first law, quantitative statement of the conservation of energy, but second law is an independent law which gives the feasibility of a process, the direction in which a process takes place. So, these things we have learned in detail or we have discussed in detail. So, similarly, the second law analysis also will come into picture to tell in which direction a reaction will take place. Sometimes it is seen that, for example, in this reaction C plus D may also react to give A plus B. So, when C plus D is formed, this will again react and will produce A plus B. The net reaction will go in which directions, whether A plus B will be depleted finally to give C plus D or in the reverse direction, which will come across these things afterwards, the direction in which the reaction will take place and also the equilibrium composition of the reactant. This is at the present moment looks like an information. This all we will come across afterwards. These are being furnished by the second law of thermodynamics. So, first we will discuss the conservation of mass and then conservation of energy. So, what is conservation of mass? Very simple, the school level concept, that in reaction no mass can be destroyed, definitely. So, therefore, mass of reactants must be equal to mass of products. So, mass of reactants must be equal to mass of products. Mass of products. So, therefore, total mass of reactants must be equal to mass of products. And as you know, when we write this chemical equation in a balanced form, let A and B are typical species, which may be element, which may be compound, C and D are also like that, then they have got some fixed number of moles to make the reaction complete. For example, we can write this way, gamma A plus gamma B. These are the recapitulations of your school level things, gamma C. This is the basic chemistry. That means that gamma A number of moles of A can react with gamma B number of moles of B. These are the sufficient condition, necessary and sufficient condition, that is gamma A, that is necessary condition you can tell. Gamma A number of moles of A can react with gamma B number of moles of B to produce gamma C number of moles of C and gamma D number of moles of D. So, these are the number of moles which are required to balance the equation. So, this reads like this, and these are known as what? These gammas are known as gamma A, gamma B, stoichiometric coefficient, which are required, stoichiometric coefficient. An example I give, very simple example, H2, 2H2 plus O2 is 2H2. So, stoichiometric coefficients are 2 gamma A 2, gamma B 1 and gamma C, gamma D, there is 1, 2. That means 2 moles of hydrogen react with 1 mole of oxygen gives 2 moles of water vapor. Similarly, C plus O2 is CO2. Here all stoichiometric coefficients are 1 for reactants and products, 1 mole and 1 mole, but this gives the mass balance. Yes, the mass of the reactants equals to the mass of the products. Another example, these are all very primary level things. For example, if you consider a combustion reaction, a fuel, methane, which oxidizes with oxygen, reacts with oxygen. So, what will be this CH4 plus O2 is, what will be CO2 plus A. How to balance this equation? Then CH4 plus 2O2 is CO2 plus 2H2O. So, therefore, you see gamma A is 1, gamma B is 2, gamma C 1, gamma D 2. So, these are the 1, 2, 1, 2 are the stoichiometric coefficient. Means 1 mole of methane requires 2 mole of oxygen to produce 1 mole of carbon dioxide and 2 mole of water vapor. That means for a complete conversion, these are the mole ratios. So, if we have to multiply them, if we have to take more moles, that means these moles are correspondingly multiplied with the stoichiometric coefficient. So, you can multiply 2, 3 by any integer in both the left hand and right hand side. But these mole ratios will be the proportions of the stoichiometric coefficient. These are the basic primary level thing. Now, let us now, what just now Professor Das mentioned, that in each cases the total mass of reactants must be equal to the total mass of the products. Okay. Now, we just first understand this thing through a simple problem, whatever we have discussed, then that will be made more clear if we go through this simple problem, this simple example problem. Let us see this problem. A fuel has a mass analysis by chemical elements. Slowly you go through the problem. A fuel has a mass analysis by chemical elements of 85% carbon. 85% carbon is the mass analysis and 15% hydrogen. 85% carbon and 15% hydrogen. These are the pertinent data. The dry products of combustion, exclusive of the water vapor in the products, that means without water vapor, the dry products show the following volumetric analysis. This is the volumetric analysis by volume. Carbon dioxide 12.5%, oxygen 2.4%, carbon monoxide 0.9% and nitrogen 84.2%. True. The atmospheric air supplied from combustion, this is the combustion reaction, rapid exothermic oxidation of a hydrocarbon with oxygen is known as combustion reaction. Combustion contains 0.028 kg of water vapor per kg of dry air. Dry air means oxygen and nitrogen. So, this is the value given. So, we have to determine per kg of the fuel, that means the analysis has to be made per kg of the fuel. the amount of atmospheric air supplied, the amount of atmospheric air supplied, the amount of water vapor in the products, and we have to write the chemical equation of the reaction. Now, how to do this problem? The problem is clear. So, problem has got 85% carbon and 15% hydrogen by mass. Okay, and the dry products show a composition by volume: carbon monoxide, oxygen, carbon dioxide, oxygen, carbon monoxide, nitrogen. This nitrogen comes from the air. Well, so these are the constituents of the products. Keep it in mind. And the atmospheric air supplied for combustion contains this much kg, that is 0.028 kg of water vapor per kg of dry air. So, we have to find out the amount of atmospheric air supplied, the amount of water vapor in the products, and we have to write the chemical equation. This type of problem is totally based on the analysis by mass. So, let me do this problem. First of all, we have to find out the number of moles. Now, if we know that 85% carbon and 15% hydrogen, so number of moles of carbon, what is the number of moles of carbon? Number of moles of carbon is per kg. Now, we make the analysis per kg of fuel. So, 1 kg of fuel, 0.85 kg of carbon. So, number of moles will be 0.85 by the molecular weight of carbon, 12. So, that this gives you the figure 0.07083. I give you the figure like that. Similarly, we can find out the number of moles of carbon per kg of fuel. I am not writing everything per kg of fuel and all these things, it will take a long space. Moles of hydrogen, I could have written by symbol also. So, 0.15 kg, 15% by mass, that means per 1 kg of fuel it will be 0.15 kg, and hydrogen molecular weight is 2. So, this will be 0.075. So, this is the number of moles of hydrogen. Well, so we can start with this. The fuel is now expressed as 0.07083 carbon plus 0.075 hydrogen, okay, H2. I better write it like this. So, this will be C and this will be H2, well, C and H2, then plus the, now air will be there. Now, we do not know anything that whether air is sufficient or air is more. Now, in this context I must mention one thing, that we know a stoichiometric chemical reaction, that for 1 mole of fuel, for example, if we consider the burning reaction or combustion reaction, this much mole of air is required. But if you use more air or more oxygen, this is known as excess air. This is usually expressed in terms of the percentage over the theoretical air. Theoretical air is the air which is required, or oxygen which is required just for the complete reaction of 1 mole of the fuel. Okay. So, in this case we do not know all these things. So, we consider A as the number of moles of the air. Okay. A is the number of moles. So, then what we do? We write A O2. Okay. O2. A is the number of moles of air, no, number of moles of O2 rather. O2, I am sorry, O2. Then this will be 3.76 A N2. So, what we assume here, A, this is an unknown, number of moles of O2, oxygen is being supplied. So, with that 3.76 nitrogen will be supplied, because nitrogen to oxygen volume ratio is 3.76:1. This has to know. This has to be known, and the ratio of volume means ratio of moles, because mole represents the volume. 1 mole of oxygen and 1 mole of nitrogen, they represent the same volume at the same pressure and temperature. So, therefore, the mole fraction is equal to the volume fraction. They are scaled by their molecular weight. Okay, the mass is scaled by their molecular weight to express the volumes or the moles. Moles are representative of the volume. So, mole fraction is the volume fraction. So, volume fraction is the mole fraction. So, 3.76. Now, this becomes equal to, now we know that now we have to assume that let B is the number of moles, let B is the number of moles. Here we have to write these things. Let B, I will write here, let B is the number of moles of number of moles of dry product, number of moles of dry product per kg of fuel. I am not writing, and X is the, with these two things we will here use the number of moles of, first you write this thing, otherwise equation you will not understand. Number of moles of H2O in the product, number of moles of H2O in the product when we use dry air, when dry air is supplied, So these two things we will have to assume, because these are not known a priori. So therefore we have to use the B as number of moles of dry air, dry product, and X is the number of moles of H2O in the product when dry air is supplied. Dry air is supplied, this H2O is formed because of the reaction of hydrogen with what? Oxygen, hydrogen of this fuel with the oxygen of the air. Now if B is the number of moles of dry product, so I can find out the number of moles of the carbon dioxide, oxygen and carbon monoxide, which are the constituents of the products, because their volumetric composition is given 12.5%. that means I can write 0.125 B into CO2, this is CO2 plus, if you do not understand any problem you can tell me, but it is extremely simple at school level things, 2.4% by volume, that means by the number of moles. B is the total number of moles of dry product, that means it will be 0.024, 2.4% into B, that will be representing the mole of oxygen. Well, then you get plus, what are other things? Carbon monoxide 9%, that means it will be 0.009 or 0.09, 9%, 0.09, 0.009, the data given is 0.9. Oh sorry, I have written here itself with the same color, it is difficult to maintain this. However, this times this CO. Well, then next is what? Next is nitrogen. Nitrogen is 84.2% plus 0.842 into B into nitrogen, and we consider X as the number of moles of H2O when dry air is supplied. First we consider the dry air, because wet air, if moisture is there, that will be added both on the left hand and right hand side, that is nothing great, but this is what is formed from the reaction, that is the water vapor generated in the product because of the reaction of this hydrogen and oxygen, XH2. So if we can write this equation in molar form, then what next? Next is your application of the conservation equation. Okay? So next is the application of the conservation equation, means conservation of mass. Now you apply the conservation of mass. Well, now you apply the conservation of mass. Now you make the conservation of mass. First you make the mass balance of C. You make the mass balance of C. I am writing only C. You make the C balance. If you make the C balance, you see that C is here, mass, and where is C? C is here and here. So therefore we can write 0.07083 equals to 0.125 B plus 0.009 B. See, there is nothing else. So this is giving explicitly B. This is an explicit equation for B, and it gives B equals to 0.5286. So we get the kg mole of dry products per kg of fuel. This again I am not writing. This, what is this? This is the kg mole of dry products per kg of fuel, as you know the nomenclature of D. Now you make H2 balance. H2 balance. Okay, H2 balance is 0.075. These are all mass balance. One thing, earlier I told that the total mass of the reactant is equal to total mass of the products, but here what I am using, this is a gross mass balance. You can track a particular element. You can track a particular element which was combined in giving some product, again in the products which is going to other product. For example, hydrogen was there initially with carbon to define the compound hydrocarbon. Now it has gone with the oxygen and to define the water vapor. So therefore, a particular element, a single individual element mass is also conserved, because that element is not being destroyed. It is being recombined to give a different compound. That is the basic definition of reaction, as you know at school. So therefore, if we track a particular element, his mass is being conserved before and after the reactions. Okay. So therefore, H2 balance, I must tell this thing before that, H2 balance gives, you just search where are the H2. So H2 is only here, X. That means straight away X is given. So therefore, I get B, I get X explicitly from the two equations. Next is O2 balance. One by one, if you make O2 balance, then O2 balance will give what? Just search, O2 is here, that means A equals to, then O2 is where? 0.125B. In the reactants only A. Here plus 0.024B plus 0.009 by 2B CO, well, plus X by 2. So B and X are known beforehand. So this gives explicitly A. Clear? And if you put the value of B and X, then I get a value of A which equals to 0.1186. So I get the value of B, this value of X, this one, and A, this one. So you can tell, sir, why don't you make nitrogen's balance? Yes. So the equation, the problem should be well posed in such a way that even if you use the nitrogen balance, it should not disturb the results, because everything is found out. If you make a nitrogen balance, I am telling you what you will get, 3.76A. So this will be a redundant equation in a sense that the balance is automatically maintained. 3.76A must be equal to, we search for this thing where it is 0.842B, and if you put this value of B, this also gives a 0.1186, but by calculation it comes 0.84. However, it does not matter. That means we can tell that as a check we can make whether the nitrogen balance is there or not with these values of A, B, X. Or other way, from the nitrogen balance we get explicitly A whether we get the same value of A or not. All right. So after this, now I start. So therefore everything is known. That means I can now substitute this A, B, C here, A here, C here, B here, so that the entire equation is written, chemical equation is written. Now we are in a position to find out all these things which have been asked for. The amount of, you just see your note, per kg of fuel, the amount of atmospheric air supplied. So amount of atmospheric air supplied, how do you find out? Amount of atmospheric air supplied, 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 simply put A, this is the atmospheric air, that means 0.1186. O2, now you put the molecular weight 32 plus 3.76 into 0.1186 into 28. That means this kg of dry air supplied per kg of fuel. So part is very simple. Next is the amount of water vapor in the products. Now amount of water vapor in the products, to find out, you may tell, sir, I know this XH2, I know X, so amount of water vapor is X into H2. So amount of water vapor, which one? 16 or 32, O2 32. So early you have forgotten these things, how I do wonder. Some 40 years back I read these things at school level, I still remember. Of course you may tell, sir, you are dealing with these things for certain other purpose. Okay, Shogata, 32. Now sometimes I know this confusion is there. For hydrogen it is all right, 1, 2, but oxygen sometimes whether the atomic weight is 16 or the molecular weight is 16. Okay, I appreciate this, it is 32, all right. So one way of remembering this thing I tell you, at my student days also this was the confusion. So I tell you the key by which I used to remember. The very first day in the school at class 9 level, we that the gravimetric composition of water is 1:8. That has to be remembered. You remember that gravimetric composition, that means the composition by weight of water vapor or H2O compound is 1:8. If this is so and hydrogen is 2, it has to be like that. So sometimes this confusion is cleared from that. Okay, I tell you. Now, amount of water vapor, amount of water vapor. Okay, amount of water vapor, can you tell, how can I find out? One is the x into H2O. So one can tell, sir, you have got the value of x. So it is as simple as this thing, 0.075 into 18, the amount of vapor in the product. But this is not the amount, plus some amount is supplied with the air. So that will be there. Now let us see what the atmospheric air supplied for combustion contains 0.02 kg of water vapor per kg of dry products. That means 0.028 into this, I have not given you the value, this value will be 16.25 kg. So therefore this into 16 point. So this will be the total water vapor. Okay, this will be the total water vapor in the products, and this value will be 1.805 kg of water vapor per kg of fuel. And write the chemical equation. So chemical equation I am not going to write, this is left to you as an exercise. Chemical equation is very simple. We put the value of here A, B and X and you get the chemical equation. But when you write the chemical equation, you don't forget, you have to write the one very important thing here, some moles of the water vapor there. How to find out the moles of water vapor? Because we have to write the chemical equation in terms of moles. So this much amount of water vapor is there with air. So number of moles of water vapor which is carried with the air, I am not writing everything, this will be this part, that means 0.028 into 16.25 divided by 18, which gives you a value, well, number of moles of air, this will give you a value of 0.025. That means when you write the equation, you will have to write here 0.025 H2O, because this will not come from here, because this is already there and this will be added here, 0.025 H2O apart from this X. I could not write this initially because I did not know this value. So therefore now putting the value of A, B and X as you have got here, A, B and X, A is this 0.1186, B 0.5286 and X 0.075, you can write the equation. So this gives you a clear idea about the mass conservation. You write the equations, chemical equation in terms of the moles, try to find out from that what are the known and what are the unknowns. You have to assume some number of moles as the unknown, which will automatically come out if you make the conservation of mass of a particular element taking part in the reactions. Then the mass balance will give you the number of moles. This is as simple as this. Okay. Now I will come to the conservation of energy or fast law analysis. Any question? Please.
Sir, the 0.025 H2O, but it is said that that much kg of water enters per kg of air.
No, not that's the kg. Kg is this one. I have divided it by 18 and this. This is the kg. You follow it clearly. So this is the kg that is being generated from the reaction, and this is by the problem 0.028 kg of water vapor per kg of dry air. This is the kg of dry air. So this is the kg of water vapor which is carried by the dry air, which is there before the reaction, after the reaction. So this gives an equivalent mole. Why? Because I will have to express in terms of mole. 18 is the molecular weight of water vapor. Okay. Now next is the important part where we will enter, which has not been taught at the school level, that the first law or conservation of energy. So before telling, going for the analysis, I tell you certain thing. Conservation of energy, or the first law, conservation of energy. Now we will be restricting ourselves here for the combustion reactions, that is the burning or oxidation of hydrocarbon with oxygen. But this is valid for all reactions to understand the physical thing. Now let us consider these things coolly, that we have a closed vessel, insulated vessel, closed insulated vessel, and in the vessels we have methane and oxygen. which the environment is conducive for burning, and consider any pressure Pi and temperature Ti, initial pressure temperature. This is an equilibrium state initially, but this pressure and temperature are such that this is conducive for burning. About this I discussed when I discussed the IC engine problem, that how the burning takes place and all these things. So for example, this is conducive for burning. Just at the outset of burning we consider this state, and we see here that the burning is completed. Let us wait for some time, because burning will take some time, and the burning will complete, and if we give the sufficient time for the burning to complete, then we have CO2 and water vapor. No CH4 will be left, because if we mix it with stoichiometric air or more than stoichiometric air, all the CH4 will be burned and make it insulated. Okay. Now you tell me, what did you observe practically? You first start with our common experience. We will see, if we do that, the pressure and temperature which will be generated will be higher than this. First start with the common experience, because thermodynamics is based on the common experience. I told you in the first class itself, all the laws of thermodynamics have been determined or have been made from the day-to-day experience from nature. So therefore we see that Tf is greater than Ti and Pf is greater than Pi. That means these temperatures are much more than the initial temperature. It is true. Okay. Similarly, if we make a system like this, closed open system, same thing. If we make an open system completely adiabatic, and you allow CH4 and O2 to enter into that section, through this section to this steady flow system where the pressure and temperatures are Pi, Ti conducive for burning, and you expect the burning is complete within this length, and you come with CO2 and H2O which have a pressure. Now in a steady flow process, I have told pressure is constant. Until and unless we take care of the friction losses, we consider the pressure to be constant in ideal case, but Tf is greater than Ti. So temperature is increased. Okay? Alright. Now if I write the first law, of thermodynamics, what we get? We write that Q is equal to, for both the cases, UF minus UI plus W. Now there is no work transfer in these cases, W is 0, and there is no heat transfer in these two cases, Q is 0, which means UF has to be equal to UI, because of the first law, the internal energy remains same. But we see, though the internal energy remains same, but the state point changes. Here the temperature is more, pressure is more. Here the temperature is more even if the pressure is less. This is our common experience. That tells that probably the reactants and the products do not have the same internal energy at the same state. Okay, that means the internal energy of the products at this state is equal to the internal energy of the reactants at this state. These two states are different, because this is Pi, Ti, Pf, Tf. Here also, the internal energy of the reactants at Pi, Ti is equal to the internal energy of the products at Pi, Tf. This is Pi, Tf. So therefore we see the internal energy of the products and reactants are not same even the state is same. Consider these two products and reactants are ideal gases. That means two ideal gases, mixture of ideal gases of different species, do not reveal the same internal energy. So we will have to brush up our earlier knowledge to change the scale of internal energy. Something we have to do, because we cannot hold that particular assumption. Now I go one step further to strengthen this view. Let us consider that I want a reaction at isothermal condition. That means I start with PiTi, CH4 plus O2 at PiTi, and I make the reaction isothermal so that I end up with CO2 plus H2O at PiTi. Now our common experience tells, if I have to do this, since with adiabatic condition the temperature shoots up, that means to make an isothermal process of combustion, isothermal and isobaric, we will have to continuously take heat, so that heat has to come out. So during the process I have to continuously extract heat, so that some amount of heat has to be taken out to make the process isothermal, and so that the initial pressure temperature, isothermal means only temperature, I also add that pressure, so that initial temperature and final temperature be equal, initial pressure and final pressure be equal. Similar is the case here, that if I have to make the process isothermal along with the isobaric, that means Ti and this Tf equal to Ti, and from our experience, as in adiabatic case the temperature shoots up, that means I will have to take out some heat out to make this condition same. That in that case Q is not 0, in that case Q is equal to UF minus Ui. W is 0 in both the cases. Sorry, in this case I am sorry, here I have written for this. If you write this for the steady flow process, this will be HF minus HI plus W from a steady flow energy equation. That means W is equal to 0. I only told in terms of internal energy. When steady flow process is there, that means enthalpies are not same. Enthalpies are same even if the state are different. Sorry, so at the same time both internal energy and enthalpy has to be thought of. So here for this process Q is UF minus Ui, and for this process Q is HF minus HI. So now this process tells that, you see, though the state point is same, but to make the state point same during reaction I will have to take out some heat, which means here Q is less than 0, because this is the equation from first law where Q is the heat added. When you write the final minus initial internal energy or final minus initial enthalpy. So when Q less than 0, this tells that UF is less than Ui or HF is less than HI. Otherwise the first law of thermodynamics will not be valid, which means that at the same state the enthalpy of the two or the internal energy of the two reactants and products are not same. Rather in this case it is less. That means the internal energy of the product is less, that is U product, final state, this final state Tf, so I write this as the product now, final state I write as the product now, and the initial state, okay, you can write F also. So the product or the final state is less than that of the initial state. The enthalpy of the final state is less than that of the initial state. So this is clear. So therefore from this we can find out one thing, that in this case the reactants and products do not reveal the same internal energy or same enthalpy when the state is same. And for this type of reaction where the temperature and pressure is increased when it is made in an adiabatic system, in a closed process, non-flow process. Similarly in a steady flow process where temperature is increased if it is made in adiabatic condition, or otherwise you can tell to make it an isothermal condition we have to take away heat. This type of reaction, the internal energy of the products of the final state has to be less than the internal energy of the reactants at the same pressure and temperature. Similar is for enthalpy. Is it clear to everybody? So therefore we see that the internal energy or enthalpy are not same at the same state for products and the reactants. With this in mind, now let us draw a curve like this and consider the ideal gas reactions where enthalpy, usually enthalpy and internal energy is expressed in terms of temperature and other property. For internal energy we usually recommend volume because it pertains to a closed system, and for a steady flow process we recommend the pressure because it is done in a steady flow process with a constant pressure process. So therefore Tp or Tv, this is the usual representation. But if we consider an ideal gas reactions, we can substantially consider that internal energy and enthalpy are functions of temperature only. And if we draw a graph, because the figure will give you the things in a more clarified way, that internal energy, for example, this is temperature, the graph go like this. This is the reactants for reactants, and for products, so this is products. Similar is the case, sorry, for H and T, so this is reactants and this is, sorry, this is products. So therefore you see at any temperature, if you draw a vertical line, at any temperature if you draw a vertical line, you see that the products and reactants and products do not reveal the same internal energy. Internal energy of the reactant is more than the product, and this intercept is the difference in the internal energy or difference in the enthalpy, and this difference in internal energy or enthalpies are known as enthalpy, internal energy of reaction, and internal energy and enthalpy of reaction. So we define this as delta UR by magnitude, delta UR and delta HR and delta HR. So this delta UR is defined as U, be careful, UP products minus UR. So the magnitude is this, but if it is defined like this, so UP is less, UR is more, so it is negative. So value is negative. So it is defined in this, so UP minus UPR. This is the internal energy of reaction at a given temperature. If it is an ideal gas at a given temperature, it will vary from temperature to temperature because the two curves may not be parallel. Similarly, delta HR is given by HP minus, this is definition, HR. And this is known as internal energy of reaction, and this is known as enthalpy of reaction. This I am not writing all these things. This is the internal energy of reaction, this is enthalpy of reaction. Should I write this? Delta UR is the internal energy of reaction, internal energy of reaction, okay, and delta HR is enthalpy of reaction, enthalpy of reaction. So you see, these are the definitions. Usually this internal energy of reactions and enthalpy of reactions at the normal condition, normal not standard condition, rather you can tell 288 K, that means 25 degrees Celsius. Here 288 K or 25 degrees Celsius, that is given as delta UR 0 and delta HR 0. They are referred to as internal energy of reaction at standard condition and enthalpy of reaction at standard condition, and usually for all practical cases these values are referred to as internal energy of reaction and enthalpy of reaction. If otherwise nothing is told, if it is told that internal energy of reaction is this, that means it is the internal energy of reaction at the standard temperature. That means it is the difference of internal energy or enthalpy of the products minus that of the reactants at 25 degrees Celsius. So henceforth always whenever we will tell that internal energy of reaction or enthalpy of reaction, we will mean this value, that means at standard condition, okay. Now you see one very interesting thing, that when the process was performed adiabatically, what happened? Internal energy constant in a closed system, that means I can show the process by a horizontal line parallel to T. That means if my initial point is this, that means through I draw a vertical line, horizontal line, this cuts here the final point. So automatically the final point gives a higher temperature. Physically what does it mean? That means this internal energy is fixed for the reactant. The same internal energy will be exhibited by the products if it can attain this temperature, otherwise not. At the same temperature there will be a difference. The product internal energy is less. Similar is the case if the initial point is this and the steady flow system, the process is caused at adiabatic condition, that means the enthalpy remains same, work transfer is not there, changes in kinetic potential energies are negligible, steady flow energy equation tells HF is HI. So the same H has to be exhibited, if it has to be exhibited by the products, it has to attain a temperature which is higher than the temperature, initial temperature of the reactants. It's very clear if we know these things. Now we can write the equations when this is not adiabatic. What happened? Okay, let us again draw these figures here. Again draw these figures, U versus T. Again draw these figures, that is the reactants, and that is the products, and again T. If you have got any question you can ask me. Reactants and products. Now it may not be adiabatic process. So let us consider I is the initial point. I is the initial point. That is I, this we can give a nomenclature R, because initial state is the state of the reactants and the final state is the state of the product. Let the final state is here, which is the state of the product. Similar is the case here. The initial state, some initial state arbitrarily I fix, some final state for the product I fix. This is the final state product. Now you see how can I write the equation. Equation is very simple. For a closed system, Q is nothing but U P, that means this point, minus UR, whatever is the internal energy here and internal energy there. So this is the difference, first law of thermodynamics. Similarly, we can write here Q is equal to HP minus HR. So this type of case, our main objective is found out the heat transfer. That means the problem is like that, if our initial state of the reactants are told in a combustion, closed system combustion, if my final state is known, I have to find out what is the heat transfer, whether heat is added or heat has been taken out, and if it is so, what is the amount. So Q is equal to UP minus UR. There is a convention to write this equation in little different form with some school level rearrangement of algebra. That means I can write this thing as UP minus UP0 minus UR minus UR0, then what I have to do, please tell me, plus UP0 minus UR0. That means this becomes equal to delta HR0, which is the, delta UR0, which is the internal energy of reaction, which is given. These are the given things. In a table we get what is this reaction, this is the internal energy of reaction. That is why I am rearranging this thing in terms of that for my easier calculations. Plus UP minus UP0 plus UR minus UR0. Okay, minus. Similarly, we can write this as delta HR0 plus delta HP minus HP0 minus HR minus HR0. Okay. So now here the most important thing is that you have to add this with this. That means try to understand that this is the 25 degrees Celsius, this line. Let this is the 25 degrees Celsius line. This is the 25 degrees Celsius line. So therefore what happens is that this is your delta UR0, this is your delta HR0. This is only algebra, nothing else. So your initial reactants may be not exactly at 25 degrees Celsius, it is away from 25 degrees Celsius. So this will be reflected here, UR minus UR0. This UR0 is the here, that means this value is UR0. Similarly, UP0 is this value, UP0. So your product finally at this state which is departed from UP0. That means the case which we discussed first, the isothermal burning, where the temperature remains same, the state remains same, that means this part and this part will be 0 in that case, because the reaction starts with this, and if that is at the standard condition, for example, that means if I condition at 25 degrees Celsius 1 atmospheric pressure, I make the reactions and I take the heat away, so that in this type of reactions where the temperature shoots up, I will have to take the heat away. So that will be automatically manifested in this equation. I make the reaction in such a way that it comes with the same temperature and pressure. That means this term will be 0, this term will be 0. In that case, you see the heat transfer is responsible for this internal. Because of this we have defined this. Now it is other way. The heat transfer is given by the internal energy of reaction and enthalpy of reaction. And the type of reactions where the enthalpy of reactions or internal energy of reaction is negative, that means the reactants have got more internal energy or more enthalpy than that of the products, then these terms are negative and heat is negative. That means heat has to come away, come out of this system. Alright, and this type of reactions are known as exothermic reaction. Henceforth I tell, I don't want to hear from any of the students who have attended this class this totally wrong and a little loosely defined terminology in practice that an exothermic reaction is the reaction which liberates heat. Heat can never be liberated. Heat is an energy that flows, or that is an energy in transit. So whenever there is a temperature difference, some kind of energy flows or some kind of energy plays in transit, which we call heat. So liberation of heat or heat is stored, storage of heat is not an acceptable word. So exothermic reaction is a reaction where internal energy of reaction or enthalpy of reaction is negative. That means the reactions for which the internal energy of the reactants or enthalpy of the reactant is more than that of the products at the same state, if it is an ideal gas at the same temperature. So reverse is there. If the reactant's internal energy or enthalpy could have been lower than the products, what we could have expected, at an adiabatic process the temperature should fall down. That's the reverse one. Okay, or to make the temperature same, you have to give the heat. Okay, that means heat is demanded from the surrounding. As because heat is demanded from the surrounding for this type of reaction, which is endothermic, and heat is being liberated to the surrounding to make the process isothermal, the loosely we tell that heat is being generated or heat is being absorbed. It is not so. It is the internal energy of reaction or enthalpy of reaction, whether positive or negative, whether reactants having more or the products having more, this quantity. So this is all right. Here another thing you must know. So therefore we see that at the same temperature of pressure, for example, the standard state, reactants and products are differing in internal energy. Where from does it come? This is not the job of a person dealing with classical thermodynamics. This is the scale we fix. But I can tell you from molecular theory that this comes from the interatomic bond, the energy, which we sometimes loosely call the chemical energy. For example, if I told that oxygen at 1 atmospheric pressure and at 30 degrees Celsius or 25 degrees Celsius, and in one compartment methane is there, you will definitely tell the internal energy of the methane is more, because chemical energy of the methane is more. But don't use the word chemical energy. Again I tell, the way I told in the beginning of these classes, that from the viewpoint of thermodynamics, apart from heat transfer, all kind of energy transfer is work transfer, whether it is an electrical energy, that passing of current across a voltage difference, whether it is a magnetic flux because of the difference in the magnetic intensity, or any other type of work, energy transfer comes under the category of work transfer. We can give that some adjective, the electrical work transfer, magnetic work transfer, mechanical work transfer, these all come into the category of work transfer. Similarly I tell, so ultimately in thermodynamics there are two forms of energy from first law. Again I recapitulate, give the two status of energy, one energy in transit, that is heat and work transfer, another energy in storage, that is internal energy. Whatever is their internal energy, that means you don't tell that the methane at same temperature and pressure and oxygen at same temperature of pressure, methane has more energy because its chemical energy is more. No, methane has got more internal energy, and that internal energy of methane is in the form of the atomic or molecular bond. That is, frankly speaking, you can think in this way, that is a chemical, sort of chemical energy, though the pressure temperature based internal energy is the same. So therefore we have to add this chemical energy, then we can, for example, if I tell the change of internal energy from this pressure and temperature to another pressure and temperature, then that will follow the same rule, Cp delta T. You have understood, but the base value is different because of the interatomic bond. So this difference in internal energy and enthalpy, this makes the reaction exothermic, endothermic, whether the temperature is increased, whether heat has to be taken out to make the process isothermal, and this. Clear? So next class I will tell you the enthalpy of formation, how this now internal energy scales are fixed. So now the question comes there, internal energy we have understood that at same state internal energies of reactants and products are different. So we don't identify which is reactants, which is products. So we have to make a uniform scale for elements and compounds to define the enthalpy, so that the enthalpy of reactions and internal energy of reactions are automatically taken care of. So that scale is defined through the definition of enthalpy of formation or internal energy of formation, which I will discuss in the next class, and I will solve a problem too. So time is up today, so I cannot discuss anymore. If any question you please ask. Any question? Okay. All right.